Euclid's Elements, Book 1, Prop 43. In any parallelogram, the complements of the parallelogram about the diameter are equal to one another. This is some new language. So it's basically saying if we have a parallelogram, AB, CD, and if we have a diameter, AC, and if we create something like this, where this line is parallel to this, and this line is parallel to this, these parallelograms are known as complements because they are around the diameter. So in this big parallelogram, these are the complements of the parallelogram around the diameter. And what we're going to prove is that this parallelogram and this parallelogram have equal areas. They may not look like the same shape, but they'll be the same size. So let's label this up here. Let's call this EF. Let's call this GH. Let's call this point of intersection K. And we're going to come up with a little bit of a shorthand. Normally we name parallelograms A, B, C, D, but there's a shorter way we can do this. We can call this parallelogram BD. We just take the opposite ends. So this could be called parallelogram BD or parallelogram AC. So with that in mind, what we're going to show is that parallelogram BK, so here's what we're going to prove, that parallelogram BK is equal to parallelogram KD, the complements about the diameter. So the first thing we're going to note is that in this big parallelogram, in parallelogram, I will call it BD, that's the big one. In BD, we have a diameter, and we know from Prop 34 that the diameter is going to bisect the parallelogram into two equal triangles. So we're going to have in this parallelogram triangle ABC is going to equal triangle ACD. Now let's look at a couple of smaller parallelograms. Let's look at EH, and then we're going to look at GF. In parallelogram GH, okay, here to here, we have, so let's do this a different color. In parallelogram EH, we can see that this triangle is equal to this triangle. So triangle AEK is equal to triangle AKH. Again, Prop 34. Now let's look at this parallelogram. In parallelogram GF, we have this triangle is going to be equal to this triangle. So triangle GKC will be equal to triangle KCF. Again, Prop 34. And now it's just left to notice that if we take this big triangle and we subtract this piece and this piece, then what's left is this piece, the complement. And in this triangle, if we subtract this piece and this piece, then what will be left is this piece. And basically, since this big triangle is equal to this triangle, and these pieces that we subtract are equal, if we subtract equals from equals, then the remainders will be equal. So let's lay this out more carefully, but if we take triangle ABC, which was equal to triangle ACD, and we subtract, let's subtract these triangles, triangle AEK, and let's subtract triangle AKH. And likewise, let's subtract these triangles, triangle GKC, and subtract triangle KCF. Then, since these are equals, and we're subtracting equals from equals twice, using common notion 3, then the remainders are equal. Namely, the remainder is this parallelogram BK. and it must be equal to the remainder of this parallelogram, the parallelogram KD. And that's what we're trying to show, that the complements around the diameter of a parallelogram are equal to one another. And since that's what we were here to demonstrate, we conclude our proof QED.